All right, in the last video, we talked about these different kind of relationships between pressure, volume, and temperature of gases, how some of them were directly related and some were inversely related. Well, we're going to do some mathematical calculations and using some formulas to do this. Okay, so this first one is Boyles Law. Okay, and Boyles Law is simply stated as P1 V1 equals P2 V2, meaning the initial pressure times the initial volume is equal to the final pressure times the final volume. That makes these inversely proportionate. Okay, as one thing gets bigger, the other thing gets smaller. Easiest way I can explain this. All right, take a balloon and blow it up, about halfway, and tie it off. Okay, now take your hands and put them around the balloon and squeeze the balloon down. Make the volume smaller. What happens? Well, the pressure goes up. Volume gets smaller, pressure goes up. And if you get enough pressure, you can pop the balloon. Okay, so that's the relationship between pressure and volume. That's known as Boyle's Law. So this is an example of what a Boyle's Law problem would look like. Okay, this is a balloon filled with helium, has a volume of 500 mils at a pressure of 1 atmosphere. You take it outside, release it, and it reaches an altitude of 6.5 kilometers. That's pretty high. Where the pressure is half an atmosphere. If the temperature has remained the same, what does the volume of the gas occupy at this height? Well, the first thing you guys have to realize, this number is not important in our calculation. All right, we don't care how high the balloon went. What we're looking at is its pressure and its volume. All right. So let's see. Initially, it says it's 1 atmosphere. Okay, so we're going to start with the atmosphere, and we said that it had 500 milliliters of volume. Okay, and then we said it went up in the atmosphere and it turned into half an atmosphere. It wants to know what the volume of the balloon is. So this is just an equality, one unknown. We know 3 of the 4 variables. All you have to do is divide by 0.5 atmospheres. This goes away. And so I'm going to take 1 times 500, which is 500 divided by 0.5. When you do so, your answer is going to be 1,000 milliliters, but you have to realize 3 sig figs, 4 sig figs, 2 sig figs, you're limited to 2. That only has 1. If you put a decimal behind it, it has 4. So how do we have to do this? Our old buddy scientific notation. 1.0 times 10 to the third, and this is milliliters. Okay, that's how you should appropriately do it. Just so you guys are aware, the Unit 9 exam will be one where it's not multiple choice. It'll be like the blanks and you have to show your work. Okay, so just prepare for that. You need to show your work. You need to observe sig figs. All right, and that's basically how those go. These are all really closely or very similar. So I'm only going to show you one example of each and give you several practice ones to do. Okay, Charles' law. Okay, so Charles' law deals with the relationship between volume and temperature. All right. Uh, Probably the easiest way I can explain this, think of like a hot air balloon. All right, so you have this big balloon. They've got the flamethrower that's heating up that air. As those molecules start moving around more rapidly, they expand. They move out from one another. Okay, so a hot air balloon isn't inflating that balloon by using a fan. They actually do at the very beginning, just because they don't want to just put the flame in there on the fabric because it would go up. But yeah, if they kind of inflate it with a fan just to kind of puff the sides out. But then after that, it's simply the flame. So just that warm air expanding and making the volume of that balloon bigger. Okay, so they are directly proportionate. Temperature goes up, volume goes up. Temperature goes down, volume goes down. So there's mathematically how it's written. V1 over T1 equals V2 over T2. This is the key, guys. In every gas law problem, the temperature must be Kelvin. Okay, it has to be. The reason why it has to be Kelvin, if you use Celsius or Fahrenheit, they can have negative numbers. And if you put negative numbers into this formula, you end up with impossible scenarios. You end up with negative volumes. There is no such thing as negative volume. Either you have a volume of gas or you have no gas. There's no negative volume. Okay, and so to convert it simple, all you do is you take the temperature in Celsius, add 273 to it, and that tells you your Kelvin temp. So must be Kelvin. All right, no options not to. So let's look at this one. It says a sample of neon gas is a volume of 750 mils at 25 degrees Celsius. What's the volume at 100 Celsius if the pressure is constant? So initial volume, 752 mils. Okay, if I add 273 to 25, that's going to be 298. Now you're going to notice I'm going to put 298.0 Kelvin, because here's the deal. If you're accurate to a tenth of a degree Celsius, you're going to be accurate to the same amount in Kelvin because the degree sizes are the exact same. Okay. Um, let's see. And we want to know what the final volume is. We do not know that. And we set it at 100.0 Celsius, so 100 plus 273 is going to be 373.0 Kelvin. All right. So once again, we have a equality, and we know three of the four variables. All we have to do is cross multiply. So this 373 Kelvin comes up here. Kelvin goes away. 373 times 752 divided by 298. You're going to be limited to 3 sig figs because of these three right here. Okay, when you do that, you should get 941, and the unit is milliliters. All right, the next one is Gay-Lussacs law. Gay-Lussacs law deals with pressure and temperature. Okay, notice that this is super similar to the last one because they are also directly proportionate. One gets bigger, the other gets bigger. One gets smaller, the other gets smaller. Best example I can give you this. Okay, back in my previous life, I was a freshman girls basketball coach. All right, and so you guys realize that state of Nebraska, basketball is a winter sport. Okay, and so I kept a bag of just basketballs, like when my team would travel around to different schools, we'd have some balls to warm up with. Okay, and so I kept those in the trunk of my car. And in the winters, it's super cold, and so what happens when the gases are cold, they're not moving around as fast, right? Well, if they're not moving around as fast, they're not pushing out on the walls of their container as much, so the pressure is actually lower. So we'd go to these places, and the girls would go in there and they'd get changed, and I'd bring the balls in, but the balls would take quite a while to warm up. And so they'd come out, the beginning of warm ups, and they'd try to bounce the balls, and they were like, the balls are flat. And I mean, technically they were. The pressure was low in them because the gas was cold. Okay, we didn't have to add air to them though because the air was still in there, it just wasn't moving around. Once you played, had them inside and bounced them around, the molecules would speed up and the pressure would increase. And it wasn't enough that you could see the volume change. And you've all done this before. You've gone to bounce a basketball and there's not enough air, the pressure's low, and it's like you can tell that it's flat. It doesn't bounce real well. Well, this is the same thing, but the deal is as they were in the building in the gymnasium, they'd warm up, and especially when you would bounce them and things, the molecules would move around faster, and the pressure would return. So anyway, here is Gay-Lussacs law: initial pressure over the initial temp, final pressure over the final temp. Once again, temp must be in Kelvin. Always, always, always for these. And so it's really just substituting in and solving for the one unknown. This is super repetitive. Not too bad. Okay, so let's see. Let's start with the initial pressure, 1.07 atmospheres. And we said it's 120 Celsius. So if I add 273 to that, that's going to be 393. And once again, since it goes to the 10th, we'll add it to the 10th Kelvin. Excuse me. We want to know what the final pressure is, 205.0. Add 273, that should be 478.0 Kelvin. Once again, we're cross multiplying and getting that X by itself. So we're going to put the 478 Kelvin over here. So 478 times 1.07 divided by 393. You're going to be limited to 3 sig figs because of those three. It's going to be 1.30 atmospheres. Kelvin cancels Kelvin, you're left with atmospheres. Okay, last one I'm going to show you right now is the combined gas law. And as you can imagine, the reason why it's called combined is because it is the three Boyles, Charles, Gay-Lussacs all combined into one. Like if we get rid of the bottom part, the temperature, well, there's Boyles, all right? If we get rid of pressure, hey, there's Charles' law. If you get rid of volume, there's Gay-Lussacs law. So honestly, you can solve any of those pressure, volume, and temperature relationships using this formula. Okay, if it doesn't mention one of the variables, or it says, like temperature remains constant, that means you can omit it. So technically, this one works for all of them. All right. And you have to use this one if you see a total of 5 variables. Okay, so we have a volume, a temperature, and a pressure. We have a new temperature and a new pressure. So, yep, we need this one that has six parts to it. All right. So let's go ahead and just add in what we know. So let's say the initial pressure is 0.974 atmospheres. Okay, and let's say the volume says it's 27.5 mils. Okay, and the temperature has to be in Kelvin. So what is it? 22 plus 273 should be 295 Kelvin. Okay, and we want to know, let's see, the final pressure is 0.993 atmospheres. We're trying to solve for the volume, so we do not know. 15 Celsius, 15 plus 273 should be 288 Kelvin. Okay, now I want to get that X by itself, so we're cross multiplying, right? You guys understand this one goes up here and this one goes down here, right? So I'm going to put the 288 Kelvin up here, and then the 0.993 atmospheres goes down here. Notice the Kelvin cancels, the atmospheres cancel, we're left with mils, right? And so all I have to do is 288 times 0.974 times 27.5 divided by 0.993 divided by 295. We're going to have 3 sig figs because there's 3 here, and there's 3 here, and there's 3 here. Those both have 4, so we're limited to 3. Your answer rounded should be 26.3 milliliters is the final volume. Okay, so I'm going to give you guys some to practice as many or as few as you need to do. Okay, we'll go over these. I'll give you the solutions Monday, and then we're going to just do a little more practice. I'm going to add a log to the fire called the ideal gas law. But once again, Boyles, Charles, Gay-Lussacs combined. Super simple, right? All right. Have a good one.